Hey guys, um, looks like we only have 20 people for this second part of Coachella. Um, I hope you guys are doing good. We'll go as long as I have people, and then if you guys aren't interested, drop off, and then I'll probably just finish and post the new material to YouTube. I've got to post last week's material. Um, uh, have been teaching a workshop all week and just haven't done it. But wanted to go ahead and tell you what to expect. Um, so we still have basically one son in Abraham, three imputation based estimators, and the fuzzy. And with those, we will be done, or I will be done. I will be done. There is still a larger number of papers, but I have just this right now. And John Roth's work was I was hoping to have that prepared for Coachella, but I wasn't able to get it together. So so let's go ahead and what we'll do is like we've done before, where we go for 45 minutes, and then real quick, let me just double check. Yep, I'm recording. So we'll go for 45 minutes, and then we'll take a break, and we'll go for 45 minutes, and we'll take a break, and we'll probably go one, two, three, four, maybe 3 or 4 hours, maybe 3 or 4 hours, um, and then we'll be done. So I've really enjoyed it. I hope that this has been useful for you. Feel free to ask questions in the stream chat, and I'll try to do my best to answer them to the best of my ability. Okay, so let's go ahead and get started. So, Son and Abraham. Son and Abraham was written by Sophie Sun and Sarah Abraham at MIT. The idea for the paper came from a comment made by Amy Finkelstein in class, is what Sophie told me. Um, she said that she noticed that sometimes when you would drop certain groups or certain dummies, really, as in an event study regression, that effects would change. And if you want to see her, if you want to see her interview, I have this really nice interview with her right here. Waiting for event studies, play in 3 acts. If you go to causal inference, the remix, and you go down here to see all, and you go to waiting for event studies, April 1st, you click on that. At the bottom, I have this really nice interview with Sophie. Um, she is en route to Berkeley for a postdoc, and then she'll be heading to Madrid for a full time position after that. And we talked about the history of the paper, how she thinks about econometrics, and her background. Oh, excuse me. So, so Sophie got this idea from Amy Finkelstein's class, and she and Sarah Abraham began working on it. And it's this really great paper that's focused exclusively on. It's focused exclusively on the. Sorry for the noise. On the event study, as opposed to Callaway Santana, which is can actually be about the event study, but he doesn't do a decomposition of the problems with the event study the way that Sophie and Sarah do, Son and Abraham do. I probably shouldn't call them by their first name. Um, they're distinguished economists, so I need to. Well, of course, calling them by their last name is almost worse. I don't actually know. Doctor, whatever, forget it. Son and Abraham is the name of the paper. So, it's a decomposition of the event study itself when estimated with two fixed effects, with differential timing. And again, the issue that we're thinking about here is, what exactly is what exactly are we trying to do when we're doing these event studies, And what parameters are we trying to estimate? Why are we doing it? And what do they mean? What do those parameters mean? What do those coefficients mean when we estimate them with a regression, two-way fixed effects regression model when there's differential timing? Okay, and large part the way that I think about it is twofold. One is we're trying to provide some evidence for the pre-trends being uh, the pre-trends showing evidence for parallel trends. That's largely what you're trying to do in an event study. I think most people will use the pre-trends and they'll say, well, look at these pre-trends. Look at these pre-trends. They're pretty similar for the two groups, therefore, or for the various groups compared to a baseline, and so therefore, so sorry. I'm gonna be yawning for a little bit. I went to bed at like 5 o'clock, but then I did this thing where I just basically laid in bed half asleep until 9, and then I passed out. So anyway, they'll use the pre-trend period to say, well, because the treatment group, or here's the treatment group, because the treatment group and the control group are traveling pretty similar, therefore parallel trends holds. And it isn't true that the pre-trends and parallel trends are the same. They're not. They're not the same. This actually here is parallel trends. So notice this is the trend for the control group through the treatment, and this is the counterfactual trend for the treatment group. And so it you're not hearing any sound, Trundling? Oh, I'm sorry, Trundling. Maybe you're muted? Maybe? Oh shoot. I hope you can figure it out. Um, so you've got this pre-trend parallelism, here, okay? And then you've got this post-treatment. Oh, it's your headphone. Good. You've got this post-treatment counterfactual trend, and that's parallel trends. So why do we do the pre-trends? We do it for two reasons. Well, we do the pre-trends for one reason, and the pre-trends are done to try to provide evidence for this. Because look, if they're traveling if they're traveling a similar path pre-treatment, the idea is over a long period of time, if they're traveling a similar path pre-treatment, therefore they would have traveled a similar path here. And it's actually got like a little bit of a synthetic control kind of argument. That's kind of a synthetic control type reasoning. It's not methodologically the same, but it's kind of got that same kind of argument, which is only units that travel similarly pre-treatment would be the ones that travel post-treatment. Okay. But under differential timing, you can't draw this picture. You can't draw this picture under differential timing. And the reason is because notice we can say what a pre-treatment period is under under the 2x2 case. We can say what a control group's pre-treatment period looks like because there's only one treatment date. When there's only one treatment date, then a control group can just simply be observed before and after. But if you've got multiple treatment dates, you can't do that. So let me show you what I mean. Do I do it here? Okay. So so look at this one. So if you've got like New Jersey's being treated at 92 and New York is being treated at 93, then and Pennsylvania is never treated, then you've got a pre-treatment period for New Jersey, you've got a pre-treatment period for New York. Who knows what? It's not, it's technically undefined what the pre-treatment period is for the Pennsylvania group. Okay. So what's normally done is to run a regression. Okay. and put into the regression. This is the most common thing people are done. We're going to kind of look at a couple of different situations that I've seen done, but this is what's commonly done. You'll put in state fixed effects, or group level, or not group level, unit level fixed effects. So if it's like state level data, you'll put in state level data. You'll put in time dummies. You'll put in a dummy for whether it's t-1, t-2, t-3. So it's actually relatively easy to do this. It's a little bit harder to think about it, but the way that you do it, the way that you mechanically do it, let me show you how you mechanically do it. So I've already deleted it. So let's look at this that Baker file. The way that you actually go about creating these leads and lags is here. Let me show you. So I'm going to create a panel, all right, where every group is treated in different periods in time: 1986, 92, 98, 04. All right. Now, how am I going to create leads and lags? How am I going to create leads and lags? So what I'm going to do is I'm going to take the year and I'm going to subtract out the treatment date. Now, the treatment date is 86, 92, 98, 04. Okay. So what I'm going to do is I'm going to create a variable called time till. What is time till? List year, treat date, time till in 1 to 10. This is what time till is. It tells you how many periods until a unit is treated. So you've got here 1980, 86, 6 years prior to treatment. 1981, 1986, 5 years prior to treatment. So what I'm going to do, where'd it go? Is I'm going to create dummies for every single relative time period. Okay? For every single relative time period. And that's going to be with this saturated model, or not saturated, where everybody is eventually treated. See, I've got here units where everybody is eventually treated. So when you're having to work with, when there is a never treated group, to create this is a little bit different. For this one right here, it works. So where I don't have any untreated periods. So what do I have here? Let's look. List year, treat date, time till, DD1, DD4 in 1 to 10. All right, that's still not enough. How's it doing it? DD star. Oh, it's called 22 to 21. So let me try it again. There we go. We'll do it a little bit different. So we'll go DD 20, DD 25. Oh, list year, treat date, time till, DD1, DD4, DD20, DD25, and 1 to 10. I hope this isn't. Yeah, there we go. All right, so look. So there's no DDs here. All right, this is referring to, what is this referring to? DD1. So this is 24 years pre-treatment, 23 years pre-treatment, all right? And then I've got here the DD20 to DD25, and that's giving me, notice here's a dummy DD20. What is DD20 describing? 5 years pre-treatment, okay? That's a dummy for -5. And what that's going to do is, so look at this, tab treat date if DD, actually I'll go tab year if DD 25 equal 1. All right. Okay, that's the DD 25. So let's go tab year if DD 4 equal 1. All right. Well, there's only one group that has that many pre-treatment leads, because DD4 is a 21-year pre-treatment, right? 21-year pre-treatment. So there's only this 1986 groups that has that many pre-treatment periods. But what if we go DD year if DD 20 equal 1? All right. Well, now we've got 4 groups that have DD 20. So this was 5 years pre-treatment. 5 years pre-treatment for the 1986 group is 1981. For the 92 group, 87. So you can see here, like, we've got 5 groups that have that many leads, but when we worked with this really long lead, we're losing states. We're losing groups, okay? So we're going to, nevertheless, though, we're going to create a series of dummies, all right? So we've got this series of dummies here that we could regress. Got this series of dummies. And the estimated regression would be to run this model. And usually what's done is people will just drop the -1 lead. They'll just drop one year before, and then everything is relative to that 1 year. That's been the historical way that it's been done. And so what are these? This is that DD -1, DD -2, DD -3, the stuff I just did. Okay? And this is the coefficients on it. This is the coefficients on it. And you'll just run the regression. Like I actually have here the regression. I can show you in just a minute. Here I run it. I run this regression on all those dummies, and I can plot it. Okay? And then I can plot it. And we'll play around with that in a moment. So that's one thing that's done. One thing that's done is people just want to evaluate these coefficients here, these gammas. Okay? They just want to evaluate those coefficients, because what they're hoping is that they can find evidence for parallel trends. So they're hoping that if all of those coefficients are 0, then they'll have confidence to believe that parallel trend would have been a good counterfactual. That trend would be a good counterfactual for what would have happened in the treatment group. It's kind of a believable approach. And then these right here, these lambdas, they're measuring dynamic treatment effects, the effect over time after the treatment. Okay? So let me show you sort of this example from this really great paper by Sarah Miller at Michigan and her co-authors. Let me just, I have got to remember what this paper is. Sarah Miller, Laura Wary, Medicaid. There's a third author, and I keep meaning to remember. Norman Johnson. All right, so it's Miller, Norman Johnson, Laura Wary, right? And what they did was they linked large scale survey data with administrative death records, and then they found for the Affordable Care Act induced rollout of Medicaid under those states that expanded their Medicaid generosity. And they used this large-scale survey data that had administrative death records, and I think they were linked to people that were on Medicaid, and they found a 9.3 reduction in annual mortality caused by Medicaid expansion. And it was driven by a reduction in disease-related deaths. And it's a really important paper. It's at the Quarterly Journal of Economics. And, it's really important because we had this earlier Oregon Medicaid experiment. This is actually an RCT. It was a lottery, and so it functions as an RC randomized controlled trial in Oregon, where Oregon also increased its generosity, but couldn't afford to put everybody on, so they did a lottery. And that paper could not find any effects on mortality. It was actually several papers, and if memory serves me right, they were not able to find any effects on mortality, I think. And I think it was because it was underpowered for something as rare as mortality. And I think it was also because not enough time might have passed when they wrote the paper. So they typically looked mainly at healthcare usage and just a few health outcomes. And the only health outcome that they found in that study that was changed as a result of Medicaid was this kind of simple depression score. It was like a self-reported level of happiness, kind of. And they found improvements. I don't know if it was true depression, but it was improvements in that measure, that little survey measure. So Sarah Miller, Norman Johnson, and Laura Wary, they look at this again and they find a 9.3 reduction in annual mortality driven by disease-related deaths. Well, how do they do this? Look at this. Look at this picture. So they are going to do these event studies. Okay, they're going to do these event study plots, and that is plotting gammas and deltas. Right. So what they've got here is this. They look at it in a couple of different steps. First, they show, did Medicaid eligibility rise? And they've got this coefficient plot on the pre-treatment leads. And, they're pretty much close to zero. They're pretty much close to zero. And then there's this large increase in Medicaid eligibility that happens at treatment. Then they look at Medicaid coverage, and they find that, when Medicaid generosity rose in the treatment states relative to the control states, Medicaid coverage also rose too. And so again, evidence for parallel trends is kind of presented here as an argument. It's like a rhetorical argument. It's got that synthetic control feature, which is if they were the same pre-treatment, they would have been the same post-treatment. And then you've got here this dynamic treatment effect. This dynamic treatment effect. It's not really, there doesn't appear to be much dynamic. So there's like this, a little bit of an immediate effect. Well, there is some dynamics. Look, so these two are different from each other. And then it falls. Uninsured status falls. So you see here again, see this is evidence of these pre-trends. These are these gamma terms, right? These gamma terms, or what I'm going to use in a little bit, they're going to be called mu. They're zero, okay? And then you've got this, large level shift. There's this large level shift change here. And then you've got their mortality evidence. And the mortality evidence is basically, this one right here, this one's kind of high. It's not different from zero, but it's kind of high. And their evidence is that, they think that there's this decline. Now, the confidence intervals do overlap here. But this is their evidence for the treatment effect. And so you've got here a couple of things. Notice a little bit of some dynamics. And you got this pre-trend, right? So differential timing complicates plotting sample averages, and so what people will do instead is they'll plot regression coefficients from that dynamic specification. What Mark Anderson, Dan Reese, and Ben Hansen did was they actually took their never treated groups. They had a large pool of never treated groups, and they just started randomizing treatment dates for their never treated group, and then they just would plot. They just would plot the never treated group with their randomized treatment dates, and they would plot them over their treatment dates, -1 to 5, 0 to 5, in this balanced picture. They impose this balance in relative time, and they just show that relative to this, never treated group, you saw that when states got medical marijuana laws, traffic fatalities fell. It's an interesting paper. And you see here the event studies look really nice. I do this in a paper that I'm working on now with Christine Durance and Melanie Goldie, and I also randomized the dates, and it looked pretty good. You see here that the never treated group was experiencing this rise, and it kept rising, and our at least for like this period right here, we kind of bend it at 50 months. At this period right here, it was the same. Maybe we should have bended it at like 20 months. This period right here, they're at least kind of like, they're not really moving the same, but like one, this is down, this is up, this is kind of flat. It's sort of like, it's real noisy is the problem. It's very noisy. But look, you can sort of see here, we find this decline that happens in the T+1 periods for the counties that get Craigslist personal section, and this is birth rates. The personal section was like a hookup section of Craigslist, like a Tinder kind of section of Craigslist before Tinder. And we find that when counties got, not that we find, sorry, this plot shows this, using the randomized treatment dates for the non-Craigslist counties, this fell and this rose. When we ran the regression, though, we found this horrible picture. Positive leads, negative coefficients. Okay? And so it really got me thinking, and we put the paper down because I didn't really have the skill. And none of us, these new papers, that project predated Sun and Abraham, as well as Callaway and Santana, and so we didn't really know what to do. I didn't know. I thought we just didn't have pre-trends, so I was like, no one's ever going to believe this, and I don't believe it either. So we put that project down. So in comes Sun and Abraham. And Sun and Abraham, remember our discussion of the event studies, okay? So what we did on Goodman-Bacon. With two-way fixed effects under differential timing, Goodman-Bacon said the static specification is contaminated, or not contaminated, biased by that heterogeneity bias, that dynamics over time. So we know that we have these biases of two-way fixed effects when you're estimating these aggregate diff and diff parameters, but we don't really know what happens with the event studies under differential timing. So Callaway and Santana proposed alternative estimators for event studies that estimate group time ATT and relative event time. But let's discuss Sun and Abraham. And Sun and Abraham is like a blend of Goodman-Bacon's decomposition and Callaway and Santana's estimator. It's sort of like a blend of the two papers. Okay, so Goodman-Bacon focused on a decomposition of two-way fixed effects to show bias under differential timing. That's what it did. Callaway-Santana proposes an alternative estimator that yields unbiased estimates of the group time ATTs, and you can then take those group time ATTs and construct T-1 group time ATTs, T-2, etc. You could aggregate them. Sun and Abraham is like a combination of the two. Sun and Abraham are going to decompose those coefficient plots under differential timing and show under what assumptions will they reflect what we think they're going to reflect, which is some measure of a average treatment on the treated, even in the pre-treatment period. And then under what conditions will it fail? What exactly is inside it? And here's what they find. They basically, in their decomposition, show that the population regression coefficients on those event study leads and lags with differential timing, when you estimate it with two-way fixed effects, just like I just did. So like this right here, that it's this coefficient right here of negative 1.5 is contaminated. Or sorry, 0.15. It's contaminated. It's contaminated with average treatment on the treateds. Like it's contaminated with causal effects from other periods. So like there's like a inside this coefficient equals the true treatment effect from the -2 period and the treatment effect from -3, -4, -1, not the 0, or actually the 0, the 1, 2. It's contaminated by all of them with some weights assigned to them. Okay, so they show that the population regression coefficient from each relative time period is contaminated by information from other leads and lags, and then they present a solution that is really just like the Callaway and Santana solution. They just arrived at it differently, and it won't have those problems. The problem is coming from, again, treatment effect heterogeneity. Under this treatment effect heterogeneity, well, it's actually coming from a couple of things, but it's really driven by the treatment effect heterogeneity. Under a situation where treatment effects differ by groups, you can end up with these positive lead coefficients, even when there is no pre-trend. And the problem is that with two-way fixed effects, you end up with these weights, And sometimes the weighted average of these underlying objects cancel out, and sometimes they don't. And it's like a bit of a knife edge that they would cancel out. But under these certain assumptions, they will cancel out every time. And so what they do is they present a 3-step regression based alternative estimator, which will address the problems that they find. All right. So let's see. Do I need anything on here? So only decomposition. Yeah, it's the only. Yeah, right. So it's the. There's another paper that does a decomposition of the two-way fixed effects by Borisak and co-authors, but published. This is the only one. The contamination of the coefficients on leads and lags by treatment effects depends on the magnitudes of the weights. Yeah. So how bad the contamination is will depend on the weights, and it'll depend on the size of those average treatment untreated. And then those weights are going to be a function of how big a cohort is. So they say, just like Andrew Goodman Bacon says, examine the weights to see how bad the effect might be, because the weights are blowing up the problem, and you can calculate the weights empirically. Look at the weights. I kind of feel like I'm not as interested in that, because I think that if you have differential timing, you just don't run two-way fixed effects. That's kind of been where I come down on it. And this right here, this examining of the weights, that really is when you have the that's when you have the when you've decided to use two-way fixed effects. But if you have differential timing, then you really probably just need to be using one of these robust estimators that we've been talking about in Coachella. So let's dive into the paper. We've already used up 30 minutes. So let's dive into the paper. Here's the notation. What I found really hard about all these papers, I've said this before, what I find really hard about all the papers is just, the potential outcomes notation. And the notation, for me, it's real easy for me to forget what each letter means, and each Greek letter, and working with set notation and things like that. It's real easy for me to kind of get lost. So I have to usually make like a cheat sheet, and then I have to carry it with me everywhere I go. And this is sort of my attempt at the cheat sheet. So when treatment occurs at the same period in time, we say that they are the same cohort. What I've been saying in my talks recently is that they share the same birthday. So any kind of group of units that share the same birthday, we're going to say they are part of the same cohort, where a cohort is the letter E. So just keep that in mind. Every time you see the word letter E, it means they're a part of the same cohort. If we bin the data, binning means creating dummies that contain multiple leads and lags. If we bin the data, then a lead or a lag, right, L, will appear in a bin. What's a bin? So a bin is like, it would be this, actually. Oops. This would be a bin. So gen bin 1 equal 0. Replace bin 1 equal 1 if dd1 equal 1. Replace bin 1 equal 1 if dd2 equal 1. Replace bin 1 equal 1 if dd3 equal 1. Right? So now I've got bin 1. It's equal 0, 1, but I combined multiple leads. Right? And I might do that all the way down. And then when I get to the end, because let's say time till if treat date equal 1986, right? There's only 6 pre-treatment periods for untreated period. There's only 6 pre-treatment periods for 1986. And then there are only 5 post-treatment periods for 2004. So I might bend the data. And say gen bin before equals 0. Replace bin before equal 1 if time till is less than -6. And then I might say gen ben after equals 0. Replace ben after equal 1 if time till greater than equal to 5. And now I might run my regression with that t minus 1, t minus 2, t minus 3, t minus 4, t minus 5 been before. T plus 1, t plus 2, t plus 3, t plus 4, t plus been after. You might end up with just like this bend regression model. Hold on, let me see. How's a cohort different from? They're the same thing. Yeah, Trungly, they're the same thing. A cohort in Sun and Abraham and a group in Callaway Santana are the same thing. I actually prefer the word cohort, but remember these papers came out at the same time. So Sun and Abraham and Callaway Santana, they're at different universities. They're writing the papers for whatever reason, kind of at the same time, even though, and they come to the same conclusions, but they don't use the same nomenclature. So Raphael says, if we have weekly level data, right? So panel data is at the week level. Do you think it makes sense to have cohorts, meaning groups of a few weeks? Well, the cohort would be the birthday, all right? Would be the birthday. So you want to group them by whether or not they have the same birthday. So this would be the week in which they were born. If you're wanting to use more aggregate data, and so maybe you want to aggregate to the month level, let's say that you aggregate to the month level, then you would want to you're going to have to make a decision about how you want to do it. But what you might do is you might say, if you were born in any week of that month, we're going to consider you to be in the same cohort. So you could do that. Does it make sense to do it? I don't have a strong answer to that. In my mind, it's arbitrary how you define a date, but I think probably the more you aggregate time, the less noisy it's going to be. That's all I really have to say on that, Raphael, is the more you aggregate in time, the less noisy it is. You sort of saw that. See how noisy this is in monthly level data? If we were looking at annual data, it wouldn't be so noisy. So that might be a way to do it, to look at it like that. I don't know if that's enough of a reason to do it, but that might be a reason to do it. Okay. Then we're going to have, does anybody have any other questions? Does that answer your question, Raphael? That's kind of what you said, right? Isn't that what you said? Groups of a few weeks? I think so. Okay. Well, next we have the cohort specific ATT, and the cohort specific ATT is going to be a word called CATT, but kind of going back to what Trungly said. This was the group time ATT from Callaway Santana. So look, it's the same thing. I want to show you this. It's the same thing as this. Group time ATT. They mean the exact same thing. Okay. Okay. So it's a cohort. All right, it's called they call it, it could just be group time. It would be like group time ATT. What's the L mean? The L is the bin, it's the lead or the lag. It's the lead or the lag. So they're expressing all of their notation in terms of relative event time. Okay, relative event time. Whereas Callaway Santana didn't start there. They didn't start at the point of relative event time. They started at the point of calendar time, and then they put everything in the bin G. Okay, but before you do the binning, you could just think of it as relative event time for a cohort, the average treatment on the treated for that cohort. just like we had with Callaway-Santana. So that would be like, for the 1986 group, what is their, so like looking back at this, here, okay, so this would be, what is the average treatment on the treated for the 1986 group in -1, right? Well, you could have done it and just said 1985, right? And that's how Callaway-Santana say it, but you could just say also in relative time, say -1. So what is the average treatment on the treated for this group, letter E, in 1984? Well, that's how Callaway-Santana say it. Son and Abraham say -2. Okay, so we've got here this -2, and then we say that's the 1986 group. So it's the same thing. They're the same thing. And then you're going to estimate. You're going to estimate the CATT, the average treatment on the treated for 1984, for 1983, for each cohort. All right, so this is for each cohort here. This is for the 1986 group, and you're going to estimate it with a regression model. And the coefficient, and I'll show it in a second, will be mu. It's just like what we did up here when I was working with the Miller paper. This is going to be the mu. I should just change this and make it just seamless throughout the whole thing. Well, we'll work with that now. So, okay. So what we're gonna be doing is we're gonna be focused on these mu's. That's what we're gonna be doing. Oh, I was wondering what I think. Hold on 1 second. We're going to be focused on these mu's, okay? So if a group is never treated, the infinity symbol is what they're going to use. So they're going to say, if you were, they're going to do two things for untreated. If you're not treated, they're going to say D = 1 if you're not treated, all right? So like that would be here. So look at this, list, year, treat, date. Let's say we want to say like list, year, treat date, time till if treat date equal 1992, right? So look, oh, it's too many. Let's see, how do I do it? And state equal 1. No. Oh yeah, that's right. It's not. Let's see, 26 maybe. So it'll be 11. There we go. All right. Well, look. Okay. So right here in 86, 92 is untreated. I can do it again. Hold on. Treat. There you go. So in 91. The 1992 group is untreated. In 92, so that's one thing they could do. They could say D equals 0 or 1. D equals 0 or 1. And that would just be referring to whether or not a group is treated in that particular year. Okay? And that's like a special kind of untreated state. It's a not yet treated situation. They're going to describe potential outcomes actually more in terms of never treated status as opposed to not yet treated status. So if a group is never treated, they use the infinity symbol. It's either going to describe the group or it's going to describe the potential outcome. So you're going to have groups like E, and they're going to be never treated. They're just going to use a completely different Greek letter for that. So that would be, we don't have a never treated group in the Baker data set. But you could imagine it. So Y infinity is the potential outcome for unit I if it had been a never treated unit as opposed to a not yet treated. And they'll actually call it the baseline. They'll call it the baseline. So other counterfactuals are possible. Maybe unit I isn't never treated, but maybe it's treated later. But the infinity symbol will be referring to a never treated state. So the treatment effects are going to be the difference between the observed outcome here relative to the never treated outcome. So this is basically saying Florida is treated. Here's Florida in some particular time period. Imagine that Florida had never been treated. Not that Florida hasn't been treated yet, but that it never had been treated. So then we take the average of treatment effects at any given relative time period to mean that. It means imagine that Florida had never been treated in T minus 1, T minus 1, T minus 2, right? Or rather, yeah. So, well, Florida was treated. They weren't treated in that period, but they weren't treated. And so it's basically going to be saying, imagine that this unit had never been treated. Imagine this unit was treated. Imagine it hadn't been treated, and then calculate the average treatment on the treated at each relative period in time. So they're not going to use the calendar time. They're going to be using L. So they're not going to use the letter T because the letter T is reserved for calendar time. And calendar time is basically the calendar time is this letter. Okay, so we'll go back to here, right? This is calendar time. This is relative time. So, everybody's got a 1980 and, but, so like if we were to do, so everybody's got a 1980, but if you looked at -6, see like tab year if time till equal -6, that's different for each group. There's 6 different, for the 6 periods before group, there's 6 different years associated with that. Okay, so they're going to use that letter L, which is time until or time after treatment, and it's just year minus treatment date, which is what I did right here. See, year minus treatment date. Okay, so let's take a break, 15-minute break. We'll come right back in just a moment, and I'll put a little music on. I'll put a little music on so that we can chill for 15 minutes. All right, see you in a minute.